Hey guys, it's Miss Carlson again, and we are going to discover the periodic table today in Chapter 5 of your textbook. We just previously went over the atomic structure in Chapter 4, and now you're going to see where all these atoms of different elements are actually arranged and located in a organized fashion. And so we call that organized way of arranging the elements a periodic table, and the periodic table is arranged by increasing atomic number. And that is very important because you need to remember makes it unique. Okay, so the atomic number is what identifies the element, makes it unique to every other element on the periodic table. Now you also need to know that they are arranged by their physical and chemical properties. And that just kind of happened by the way the arrangement was set up by Mendeleev in the past. He actually did a very good job of predicting how elements would fit together according to different properties that he had found in previous elements. Okay, so one way that the elements are grouped are as metals, nonmetals, and metalloids. I suggest in your Cornell notes that you go ahead and make yourself a little table or a little T-chart and label one in group, one in properties. Metals, nonmetals, and metalloids are the three groups we're looking at. Some of the key things for each group, for metals that would identify them: shiny, they're opaque, they're good conductors, and they're also very malleable, which means you can manipulate or bend them pretty easily. Then if we're to look at your nonmetals, they're kind of the opposite. They are poor conductors. They're not malleable, so they're not really easily bendable without breaking, which makes them very brittle. Now, if you think about things that are nonmetals, I instantly think of rubber, which is made up of different nonmetal elements. And rubber is usually what is on the handles of our metal pots and pans, so that that metal cannot conduct heat through the handle and burn you. Lastly, you have your 6 elements that are considered metalloids. They actually make up a little staircase section of the periodic table that I'll show you in a second, and they have characteristics of both metals and nonmetals. So their weak conductors can sometimes be used as a semiconductor, but not, on a regular basis. Here is a picture of the periodic table, and they kind of pulled out some of your common elements that you are probably familiar with. You got your silver here and examples of what they are used to make or create. Carbon actually is what produces diamonds for us. And you have your helium and the balloons. Things that are very common and things that you've seen before to kind of help you connect with the elements in the table. Now what I want you to get out of this is the key here. You have metals, metalloids, and nonmetals. And if you take a look, which one of these groups makes up the majority of the periodic table? I hope you said metals. I know it's kind of hard to make a distinction between this pink and yellow color, but all of these are metals. Okay? And the number are going to be that staircase that I said that makes up the metalloids. We have our nonmetals here and hydrogen. Okay? Alright, so you need to know how, or what we call the rows and columns in a periodic table, and a horizontal row is going to be labeled as a period. So that's going from left to right. Okay, you see there's 1, 2, 3, 4, 5, all the way to 6, 7 periods. And when we see properties gradually change across any period, we call that a periodic trend or a law. So one example of that is how atomic size is actually going to get smaller as you move from left to right. So you can see here we have the size of the atom here, and as you go left to right, it gets smaller. We're not necessarily talking about the mass, okay? That's a little different, and we'll kind of talk more about that later. But that's just one example of a trend or law in the periodic table. A group then is going to be a vertical column. So here you have group 1, which is the alkaline metals, group 2, alkaline earth. This whole section here is made up of several groups or columns, 3 through 12. They are the transition metals. And then we kind of have a few groups that have no common name. Then you have 16, 17, and 18. Those vertical columns, they all have properties that are similar. and that's why they are in together in those groups, or sometimes also called families. Here is a picture of periodic table showing you both the arrangements. You can also see a group here that you'll come to know as the intertransition metals, because they're actually pulled out of the table out of convenience for no other reason but that. And again, I'll talk more about that in a second, but this just gives you a clear look of how many periods there are. There are 7, and there are technically 18 groups, but sometimes we don't count these group numbers, and we'll just go, this is group 1, 2, didn't mean to move yet, 3, 4, 5, 6, 7, and 8, and again, we'll get into that more later on. So I just want to break down each group for you real quick. So again, you're probably going to need to pause to make sure you get all the pertinent information, because I'm going to go pretty fast. The alkaline metals again are in group 1. They're discovered early in human history, and people noticed that they mixed ashes with water, produced a slipperier solution useful for removing grease. They described those solutions as being alkaline, which led us to the name alkaline metals for those group 1 elements. Then the alkaline earth metals are comprised of group 2. They also form alkali solutions when mixed with water. The difference with them, though, is that they're fire-resistant substances, and the alchemists kind of referred to these elements as earth, and hence we put the two together and you get alkaline earth metals. You have your chalcogens. They are composed for group 16, or sometimes we'll refer to them as group 6. Their name comes from the Greek word meaning ore forming. And some of your common ores are oxygen and sulfur. Sulfur is completely identifiable gas-wise when you're kind of driving down the road or walking around somewhere, you smell that really horrible rotten egg smell. That's sulfur. Halogens make up group 17 or group 7. They come from the Greek word meaning salt forming, because these elements have a tendency to form salts. They also are helpful in making tungsten filament glow brighter without burning quickly. Specifically, we're talking about iodine and bromine. And they're actually useful in making our halogen lamps that form the headlights of our cars. That really nice bright light is very helpful, you know, at certain times driving at night or in bad weather. Finally, our noble gases, group 18 or group 8, they're all unreactive gases. They do not combine with other elements, which is where they get their name, because people of nobility in earlier times were above interacting with common folk. So you could say that the elements in group 8 are above interacting with other elements, but it's really because of their chemical nature or properties, not for any other reason. And there's kind of a picture of a man putting the noble gases to use. And make sure you're awake there. Kind of reminds me of that Up movie. I like that movie a lot. It was cute. Then the last thing we're going to talk about are the transition metals. They make up that block that I told you is kind of like a bridge between group 1 and 2 and 3 through 8. And they're called the transition metals. They do not form alkaline solutions with water. They are harder and less reactive, and that's why we use them for structural purposes. And again, they're called transition metals because of their central position in the periodic table. So a lot of reasons for the names has to do with the position on the periodic table, and you'll kind of find that, or you probably have already found that noticeable as we go through these groups. The transition metals include many well-known elements: iron, copper, nickel, chromium, silver, and gold. There's also many lesser-known elements like titanium, molybdenum, and manganese. They are important for people that have had hip replacements, and because of their non-corrosive properties, they are good metals to use in those hip replacements, and that's kind of a cool x-ray there showing you the implant of that hip replacement. The intertransition metals, again, are the 6th period and the 7th period, and they are simply removed, like I said, for convenience. If we did not remove them, they would actually extend the periodic table out so far they wouldn't fit as a little handheld, easily read piece of reference information. So you can see here the Lanthanides and the Actinides, and if you look, and let me get my marker here, right here is where the numbers get cut off. You have 57 to 72. Well, 58 through 71 are right here. And the same thing, 89 to 104. 90 through 103 are down here. So they're just pulled out for convenience, nothing else. Now, the sixth period is called the Lanthanides because they follow lanthanum, or La. They have similar properties, and because they have similar properties, they're usually found together in the same location, kind of mixed together. They are very difficult to purify or separate from each other, but they do have some commercial use in LEDs, specifically for laptop computer monitors. But we do know that these little LEDs, these little bright lights, are used in many things. You know, your remote controls, lots of toys that your younger brothers or sisters might play with. They usually have like a power button. When it's on, it turns red. Those are all LEDs. And then finally, your seventh period is called the Actinides. They follow actinium, and they also have similar properties and are difficult to purify. They are helpful in the nuclear power industry and requires purified samples of uranium and plutonium. Now the problem comes in is, as I already told you, that they are difficult to purify. So that's where the nuclear power industry needs, a lot of resources in order to produce the energy that is very useful in our society today. Now the actinides that are heavier than uranium, so anything past uranium on the periodic table, you need to be aware that those are man-made, not found in nature. We've created them. They generally don't last very long. So we'll talk a little bit about those more later, but not in a whole lot of detail. We're more concerned about the natural elements in the periodic table and how the table is arranged. So we are done with our notes. I know that was very fast, so please take advantage of the pause and play button. Take good Cornell notes, and I will see you next time. Have a good day.